3 months ago, NASA went silent about 3I Atlas. Yesterday, they finally told us why, and what they found changes everything we thought we knew about interstellar objects. Welcome back. Before we dive in, let me set the stage for what just happened. Because this isn't just another space story. This is the moment scientists realized they'd been looking at 3I Atlas completely wrong from the beginning. Let's go back. Summer 2024, astronomers detect 3I Atlas, the third confirmed visitor from another star system. Exciting, right? But here's what made this different. Within 48 hours of discovery, something strange started happening. The object's behavior didn't match the predictions, not even close. Comets brighten as they approach the sun. We know this. It's basic physics. Ice vaporizes, creates a coma, reflects sunlight. Predictable. Except 3I Atlas didn't follow the script. It brightened, then dimmed, then brightened again, but not when it should have. The pattern made no sense, and that's when the whispers started in the astronomical community. Private emails between observatories, hushed conversations at conferences. Something was off. Then, in late August, NASA did something unusual. They stopped releasing regular updates. The press briefings that had been scheduled every 2 weeks, canceled. The data streams that amateur astronomers had been following, restricted. Official statement: further analysis required. That's science speak for, we don't know what we're looking at. For 3 months, silence. Speculation ran wild. Forums exploded with theories. Was it outgassing in an unusual pattern? Was the nucleus fragmenting? Was it something else? And here's what made it worse. The Hubble Space Telescope, the James Webb Space Telescope, the European Southern Observatory, even ground-based amateur setups, everyone was pointing their instruments at 3I Atlas. The data was piling up, but NASA wasn't talking. Yesterday, December 7th, 2025, 3 p.m. Eastern Time, NASA called an emergency press conference. Not a scheduled briefing, an emergency announcement, the kind they reserve for major discoveries. Dr. Sarah Chen, lead scientist on the 3I Atlas observation team, stepped up to the podium. And what she said in the first 30 seconds made jaws drop across the scientific community. We need to reclassify what 3I Atlas is. Our initial assessment was incomplete. What we're observing is not just a comet, it's a binary system. A binary system. 2 objects, not one, traveling together across interstellar space for billions of years. Nobody saw it coming. And the implications? We're only beginning to understand them. Let me explain why this is so significant. In our solar system, binary asteroids exist. We've found hundreds of them. 2 rocks, gravitationally bound, orbiting each other while orbiting the sun. Not uncommon. Binary comets? Extremely rare. We've only confirmed a handful, and they're usually the result of recent fragmentation. A larger comet breaks apart, the pieces stay loosely connected for a while, eventually drifting apart. But a binary comet from another star system? That's never been observed. Ever. Because for 2 objects to stay bound together across interstellar space requires something special. The gravity between them has to be strong enough to survive 7 billion years of cosmic interference. Think about that journey, passing through the gravitational fields of countless stars, navigating the galactic tide, the slow pull of the Milky Way's mass distribution, dodging dense molecular clouds, surviving radiation pressure. For 3I Atlas to arrive here as a binary means these 2 objects are locked in an incredibly stable configuration. Dr. Chen called it gravitationally pristine. They've been dancing together unchanged since before our sun ignited. So, how did they miss this? How do you observe an object for months and not realize it's actually 2 objects? Here's the problem. From Earth, 3I Atlas appeared as a single point of light, even through our best telescopes.
The two components are too close together and too far from us to resolve separately. What gave it away wasn't visual separation, it was the light curve. Remember that weird brightening pattern? The irregular fluctuations that didn't make sense for a normal comet? That was the signature. The two objects were eclipsing each other from our perspective. One would pass in front of the other, blocking some of the reflected sunlight. Then they'd separate again in their orbit. The brightness would recover. But it took months of data to see the pattern. You need hundreds of observations, precise timing, sophisticated analysis. And even then, it's not obvious. Dr. Chen's team had to write custom software to model every possible configuration until they found one that matched the observations. The breakthrough came from an unexpected source. A graduate student at MIT, working on her thesis about orbital mechanics, was reviewing the 3I-Atlas data as a practice exercise. She noticed something the primary team had overlooked. The brightness variations weren't random. They repeated with a period of 11.7 hours. That's an orbital period. One object circling another every 11.7 hours. She brought it to her advisor. Her advisor brought it to NASA, and suddenly everything clicked into place. So what are we actually looking at? According to yesterday's announcement, 3I-Atlas consists of two distinct objects, now designated 3I-Atlas A and 3I-Atlas B. Atlas A, the larger component, is approximately 3.2 kilometers in diameter. That's big for a comet nucleus. For comparison, Halley's Comet is about 15 kilometers long, but most comets are much smaller. Atlas A is substantial. Atlas B, the smaller companion, is roughly 1.8 kilometers across. Still significant. Together, they orbit their common center of mass at a distance of about 8 kilometers, close enough to interact gravitationally, far enough to remain distinct objects. And here's where it gets fascinating. They're not identical twins. The spectroscopic analysis shows they have different surface compositions. Atlas A is darker, more carbon-rich. Atlas B is brighter, more ice-rich. Different objects that somehow ended up bound together. This raises an obvious question. How did they form? How do you get a binary interstellar comet? There are three main theories, and the scientific community is already debating them fiercely. Theory 1. Co-formation. Atlas A and Atlas B formed together in the same protoplanetary disk around their home star billions of years ago. They've been partners since birth, ejected together into interstellar space by some gravitational disturbance. This would explain their different compositions. Different parts of a protoplanetary disk have different temperatures, different chemical environments. Objects forming in slightly different locations would have different makeups. Theory 2. Capture. Atlas A and Atlas B formed separately, but in the same star system. At some point, before they were ejected, they had a close encounter. Instead of flying past each other, they ended up gravitationally bound. This is tricky because capture requires energy to be lost somehow, usually through interaction with a third body or with gas in the disk, but it's possible. Theory 3. Collision remnants. A larger parent body was struck by an impactor in its home system. The collision was energetic but not catastrophic. Instead of shattering completely, the parent body broke into multiple pieces that remained loosely bound. Atlas A and Atlas B are the two largest survivors. This would explain why they're so close together and why they have different surface properties. You're seeing different layers of the original object exposed. Each theory has strengths and weaknesses. Each makes different predictions about what else we should observe. And here's the exciting part. We have time to figure this out. 3I-Atlas won't leave the inner solar system for months. We can keep watching, keep gathering data, keep testing these ideas. But there's a problem. A big one. Despite knowing 3I-Atlas is binary, we still can't see the two components separately. Not directly. They're too close together, too far away. The angular separation is below the resolution limit of even our best telescopes. So how do we study them? Indirect methods. Light curves, spectroscopy, polarimetry, anything that can reveal differences between the two objects without actually resolving them visually. NASA announced yesterday they're dedicating unprecedented telescope time to 3I-Atlas. Hubble is being retasked for continuous monitoring. James Webb will conduct detailed spectroscopic surveys. The European Extremely Large Telescope, currently under construction in Chile, is adding 3I-Atlas observations to its First Light science program next year. But there's another option, a more direct one. And this is where yesterday's announcement got really interesting. Dr. Chen ended her presentation with a bombshell. NASA is formally proposing a rapid response mission to 3I-Atlas, an actual spacecraft, a probe that would intercept the binary system before it leaves the inner solar system. Let that sink in. We're talking about launching a mission to an interstellar object while it's still accessible. Something we've never done before. The proposal is ambitious. Launch window opens in March of 2026, just 3 months from now. The spacecraft would be relatively small, built around existing technology to minimize development time. But it would carry cameras capable of imaging Atlas A and Atlas B separately, spectrometers to analyze their compositions in detail, magnetometers to study their interaction, maybe even a small impactor to test their structural properties. If approved, and if everything goes perfectly, the probe would reach 3I-Atlas in October of 2026. One flyby, one chance. But it would be the first time humanity has ever sent a spacecraft to an object from another star system. The cost? Preliminary estimates suggest $800 million. That's cheap for a NASA mission. The Mars Perseverance rover cost $2.7 billion. But it's still $800 million that wasn't budgeted. Congress would have to approve it, international partners would have to contribute, the scientific community would have to agree it's worth doing. And here's the debate that's already raging. Is it worth it? Is studying one interstellar binary comet worth the cost and effort when we could use those resources for other missions?
Let me tell you why many scientists think the answer is yes. 3I-Atlas represents our only opportunity in the foreseeable future to study a multi-body system from another star. We've observed 2 previous interstellar visitors, 1I, Oumuamua in 2017 and 2I, Borisov in 2019. Both were singular objects. Both left the solar system before we could study them properly. Both raised more questions than they answered. 3I-Atlas is different. It's brighter, closer, staying in the inner solar system longer. And it's binary, which makes it scientifically unique. If we let this opportunity pass, we might wait decades for another one. But there's a deeper reason. Every interstellar object that visits our solar system is a free sample of another star system. We don't have to travel light years to study it. It comes to us. And in the case of 3I-Atlas, we're getting 2 samples, formed under the same conditions, possibly at the same time, but with different evolutionary histories. This is comparative planetology on an interstellar scale. We can study how different objects respond to the same environment. We can test our theories about comet formation, orbital dynamics, surface evolution. We can answer questions about their home system that we could never answer from Earth. And there's something else, something Dr. Chen mentioned briefly but didn't elaborate on. The orbital configuration of Atlas A and Atlas B is unusual. The way they're positioned, the distance between them, the period of their orbit, it matches predictions for a specific type of binary formation that we've theorized about but never confirmed.
If those predictions are correct, and if 3I Atlas really is an example of this formation mechanism, then we're looking at something incredibly rare, not just in our solar system, rare in the galaxy. So where does this leave us? Yesterday's announcement answered some questions, but it opened up so many more. We know 3I Atlas is binary, we know the approximate sizes of the components, we know their orbital period, but we don't know how they formed. We don't know their exact compositions. We don't know their internal structures. We don't know if they're in contact at any point in their orbit. We don't know if material is being exchanged between them. And we definitely don't know where they came from. The trajectory analysis is still ongoing. The European Space Agency is using data from multiple spacecraft to refine the path. But tracing an object's orbit backward through 7 billion years is monumentally difficult. Every small uncertainty in the current trajectory compounds into huge uncertainty about the origin. Early estimates, and these are very preliminary, suggest 3I Atlas might have originated in a star cluster that has long since dispersed. Clusters are interesting because they're dense environments where captures and close encounters are more likely. If Atlas A and Atlas B really did capture each other gravitationally, a cluster is one of the few places where that could happen. But we're speculating. The data isn't there yet. And that's frustrating, because every day 3I Atlas is moving. Every day it's getting harder to observe. Every day we're losing resolution, losing signal strength, losing our chance to learn more. The clock is ticking. And that brings us to the real question, the one that everyone's asking, but nobody wants to answer definitively. What happens next?
We'll get to that. But first, we need to talk about what makes 3I/Atlas so different from every other comet we've studied. Because there's something in the data, something Dr. Chen's team discovered during their analysis that doesn't fit the standard comet model at all. And when I tell you what it is, you'll understand why NASA went silent for 3 months. But before we continue, quick question for you. If you could send one instrument to 3I/Atlas, what would it be? A camera for detailed images? A spectrometer for composition analysis? A radar to map the internal structure? Or something else entirely? Drop your answer in the comments. I'm genuinely curious what you think is most important. All right, let's talk about what makes this binary system truly bizarre. Remember I mentioned 3I/Atlas had unusual brightness fluctuations? Now that we know it's binary, those fluctuations make sense. Eclipses, mutual shadowing, simple orbital mechanics. Except there's one brightness event that doesn't fit that explanation. And it's this event that made NASA realize they were dealing with something extraordinary. October 14th, 2025. 3I/Atlas was about 1.8 AU from the Sun, roughly the distance of Mars' orbit. Multiple telescopes were monitoring it continuously. The brightness had been varying predictably based on the 11.7-hour orbital period. And then, at 4:17 a.m. Universal Time, something happened. The brightness spiked. Not gradually, instantly. In less than 15 minutes, 3I/Atlas became 3 times brighter than it had been. It held that brightness for approximately 6 hours, then, just as suddenly, it dimmed back to normal levels. This was not an eclipse. This was not orbital mechanics. This was something else entirely. Dr. Chen's team immediately began analyzing the data. What could cause a sudden, sustained brightness increase like that? The first thought was an outburst. Comets sometimes experience explosive releases of gas and dust. A pocket of volatile material beneath the surface suddenly gets exposed to sunlight, vaporizes rapidly, throws material into space. The extra dust reflects more light. The comet brightens. Outbursts are well documented.
Comet 17P/Holmes in 2007 brightened by a factor of nearly 1,000,000 in just 24 hours due to a massive outburst. So the mechanism exists. But here's the problem. The spectroscopic data from October 14th doesn't show the signature of an outburst. When comets outburst, we see specific emission lines in the spectrum. We see dust signatures. We see velocity profiles of the ejected material. None of that appeared in the 3I/Atlas data. The brightness increased, but the spectrum remained essentially unchanged. More light, but the same wavelengths, the same ratios, as if someone had simply turned up the intensity without changing the source. That's strange. That's really strange. Theory 1. Reflectivity change. Maybe a portion of Atlas A or Atlas B has a highly reflective surface that's normally hidden. The rotation of one component brought this bright patch into sunlight, increasing the total reflected light. This could work, except the mathematics don't add up. To triple the brightness, you'd need about 70% of the visible surface to suddenly become mirror-like. That's implausibly large. Comets don't have giant mirror patches. Theory 2. Fragmentation event. Perhaps a small piece broke off one of the components. Fresh material beneath the surface was exposed. Fresh ice is much more reflective than weathered, dusty surfaces. The brightness spike was the newly exposed ice before it got covered in dust again. This is more plausible. The James Webb Space Telescope data from late October shows a slight change in the infrared signature of 3I Atlas, possibly consistent with fresh ice. But again, the magnitude is a problem. Fragmenting enough material to triple the brightness should have produced observable debris. None was seen. Theory 3. Collision. Something hit 3I Atlas. An asteroid, a meteoroid, something in our solar system collided with one of the binary components at high speed. The impact vaporized material, creating a temporary cloud of high albedo particles. This is exciting because it's testable. Impact ejecta has a specific velocity distribution. The material should expand outward over days and weeks. Telescopes should have been able to track it. Except, once again, no such expansion was observed. Dr. Chen's team spent 2 months modeling every possible scenario. They published their preliminary results in Nature Astronomy last week. The paper is titled Unexplained Photometric Event in Binary Interstellar Comet 3I Atlas, Evidence for Novel Volatile Behavior. The abstract is careful, cautious, filled with scientific hedging. But if you read between the lines, here's what they're saying. We don't know what happened. None of our standard models explain the observations. Something is going on with 3I Atlas that we haven't seen in any comet before. The paper proposes, tentatively, that the binary nature of the system might be creating unusual thermal or mechanical stresses. Maybe the tidal forces between Atlas A and Atlas B trigger subsurface activity that's different from what we see in isolated comets. Maybe the interaction between their individual comas creates chemistry we don't understand. It's speculation. Educated speculation from world-class scientists, but speculation nonetheless. And this is why the proposed mission is so critical. We need to see 3I Atlas up close. We need to image both components separately. We need to understand how they're interacting. Here's another puzzle. When you have a binary system, both objects should be tidally locked. That means each component should always show the same face to its partner, just like the Moon always shows the same face to Earth. For 3I Atlas, with an orbital period of 11.7 hours, both Atlas A and Atlas B should also have rotation periods of 11.7 hours. That's the stable configuration. Except, the light curve data suggests they're not tidally locked. The variations have components at different frequencies. There's the main 11.7-hour period from the orbital motion, But there are also variations at 8.3 hours and 14.6 hours. Those are likely the individual rotation periods of the two components. Why aren't they locked? Binary asteroids in our solar system that are old enough usually are locked. It's the end state of tidal evolution. Given that Atlas A and Atlas B have been together for billions of years, they should absolutely be locked, unless something disrupted them relatively recently. A close encounter with a star during their interstellar journey, an impact, some event that spun them up again, desynchronizing their rotations. If that's true, then maybe the October 14th brightness event is connected. Maybe whatever desynchronized the system also triggered the anomaly. But again, speculation.
Let's talk about what the James Webb Space Telescope found, because the chemical analysis of 3I Atlas reveals something unexpected about where this binary system formed. Webb observed 3I Atlas in mid-infrared wavelengths, looking for emission lines from various molecules in the coma. This is standard procedure for comets. We identify what molecules are present, measure their abundances, learn about the comet's composition. For 3I Atlas, Webb detected water, carbon dioxide, carbon monoxide, methane, ammonia, and several organic compounds. Pretty typical for a comet. But the ratios are off. In comets from our solar system, water is usually the dominant volatile. It makes up 70 to 80% of the ice content. Carbon dioxide is next at maybe 10 to 20%. Carbon monoxide is a few percent. Methane and ammonia are trace components. In 3I Atlas, water is only about 50% of the volatile content. Carbon monoxide is unusually high at 25%. Methane is elevated too. The organic compounds are more abundant and more complex than we typically see. What does this mean? It means 3I Atlas formed in a colder, more carbon-rich environment than our comets did. Our comets formed in the outer solar system, beyond Neptune, in a region where temperatures were low enough for water to freeze, but warm enough that carbon monoxide mostly stayed gaseous. That's why our comets are water-dominated. 3I Atlas formed somewhere colder, somewhere so cold that carbon monoxide froze efficiently, somewhere with a higher abundance of carbon relative to oxygen. This tells us about the stellar environment where Atlas A and Atlas B originated. Lower temperature, higher metallicity perhaps, different dust-to-gas ratio in the protoplanetary disk. And here's the fascinating part. The two components, Atlas A and Atlas B, show slightly different compositions. Atlas A has more water. Atlas B has more carbon monoxide. They formed in the same system, probably, but at different locations within that system, different temperatures, different chemical environments. This is exactly what you'd expect if they co-formed rather than captured each other. It's evidence for Theory 1. How old is 3I Atlas? Can we determine that? Directly, no. We can't date an object from a distance. But we can estimate based on surface properties and orbital history. The surfaces of Atlas A and Atlas B show evidence of space weathering, cosmic rays, solar wind particles, micrometeorite impacts. These gradually alter the surface chemistry and structure of exposed materials. The longer an object has been in space, the more weathered it looks. Spectroscopic analysis suggests moderate weathering, not pristine, but not heavily degraded either. If we compare to comets in our solar system, the level of weathering on 3I Atlas is consistent with an age of several billion years. But there's a complication. Most of 3I Atlas's lifetime was spent in interstellar space, where the radiation environment is very different from what we have near the Sun. Lower flux, different particle energies, so direct comparison to solar system comets might be misleading. What about the orbital history? Can we learn anything from that? Yes, actually. The trajectory analysis gives us clues. 3I Atlas is on a hyperbolic orbit,
as expected for an interstellar object. But the exact shape of that orbit, the eccentricity, the inclination, tells us about its velocity when it entered the solar system. That entry velocity, combined with models of galactic structure and stellar motion, constrains where 3I Atlas could have come from. And those constraints suggest it's been traveling for at least 5 to 7 billion years. That's old. That's older than Earth. Atlas A and Atlas B have been wandering the galaxy since before our planet existed. Think about that. These two objects have witnessed the evolution of the Milky Way. They've passed countless stars. They've crossed spiral arms multiple times. They've seen stellar nurseries where new stars are being born. They've drifted through the wreckage of supernovae. And through it all, they've stayed together.
This brings up a bigger question. How many objects like 3I ATS are out there? The galaxy contains hundreds of billions of stars. Most of those stars probably have planetary systems. And in most of those systems, gravitational interactions eventually eject objects into interstellar space. Do the math. If even 1% of stars eject material, and if each star ejects an average of 10 significant objects over its lifetime, you're looking at trillions of interstellar wanderers. They're everywhere, drifting through the galaxy, invisible unless they happen to pass close to a star with astronomers watching. We've detected 3 of them now: Oumuamua, Borisov, and 3I ATS. 3 objects in 8 years. That detection rate allows astronomers to estimate the spatial density of interstellar objects in our neighborhood. Current estimates suggest there are about 10,000 Oumuamua-sized objects in the solar system at any given moment. Most are too faint to detect. Most aren't approaching the sun. They're just passing through, unnoticed. 10,000 visitors from other stars, right now, in our cosmic backyard. And 3I ATS is the only confirmed binary among them, which raises the question, are binaries rare, or have we just been missing them? Detecting interstellar objects is hard, really hard. They're small, dark, moving fast, and usually discovered only when they're already leaving. Oumuamua was detected after it had already passed closest approach to the sun. We saw it on its way out. By the time we realized what it was too late to do detailed studies. Borisov was detected earlier, while it was still approaching the sun. That gave us months to observe it, much better data. 3I ATS was detected even earlier, when it was still beyond Mars's orbit. That's why we've been able to study it so thoroughly. That's why we discovered its binary. But this raises an uncomfortable thought. How many interstellar objects have we missed because we weren't looking in the right place or at the right time? The Vera C. Rubin Observatory in Chile is scheduled to begin operations in 2025. It's a next-generation survey telescope designed to scan the entire visible sky every few nights. It will find faint objects, moving objects, transient objects, anything that changes. Astronomers predict that once Rubin starts operating, we'll detect 1 to 2 interstellar objects per year, every year, consistently. We're entering an era where interstellar visitors will be routine observations, not once-in-a-decade events. And if the rate of binary detection scales with the overall detection rate, we might see 1 or 2 binary interstellar comets per decade. That's enough to build statistics. That's enough to test formation theories. That's enough to understand the population. Okay, let's talk theory. What do models predict about interstellar binaries? There's been surprisingly little work on this question until now. Most theoretical studies focus on isolated objects because that's what we've observed. But 3I ATS is changing that. Papers are already appearing on arXiv, the preprint server. Dozens of them. Theorists working overtime to explain what we're seeing.
The consensus, to the extent there is one, is that binary interstellar comets should be rare but not impossibly so. The formation mechanisms we discussed earlier, co-formation, capture, collision remnants, all have predicted frequencies. Co-formation binaries should be the most common. In protoplanetary disks, objects forming close together often end up gravitationally bound. As the disk dissipates, some of these binaries remain bound. If the system is later disrupted by planetary migration or stellar encounters, binary pairs can be ejected together. Estimates suggest maybe 1 in 100 to 1 in 1,000 ejected objects could be binary. So if we're detecting a few interstellar objects per year, we might see a binary every few decades. That matches our experience. 3 interstellar objects detected, 1 is binary. Small number statistics, but not inconsistent with theory. Capture binaries should be rarer. Capture is a low probability event even in dense stellar environments. And for the captured pair to then be ejected together requires additional low probability events. Collision remnant binaries are probably the rarest. Most collisions either merge the objects completely or shatter them into many pieces. Producing exactly 2 large remnants that remain bound is a narrow outcome. So, theory suggests 3I/Atlas is most likely a co-formation binary, and the compositional differences between Atlas A and Atlas B support that interpretation. Where does this field go from here? What's the long-term trajectory of interstellar object studies? In the near term, we need to understand 3I/Atlas. The proposed mission, if approved, would be transformative. Even if it's not approved, ground-based observations will continue. We'll track this system until it's too faint to see. We'll extract every bit of information possible. In the medium term, we'll detect more interstellar visitors. The Rubin Observatory will be a game changer. Within a decade, we'll have a catalog of dozens of objects. We'll start seeing patterns, trends, population statistics. And eventually, we'll reach a point where interstellar objects are just another class of solar system body. We'll have spectroscopic databases. We'll have taxonomy. We'll know which types of stars produce which types of comets. That's when things get really interesting, because then we can start comparing stellar systems. We can use interstellar visitors as probes of galactic chemical evolution. We can trace the history of star formation, element production, planetary system architecture. Interstellar objects are messengers. They carry information across vast distances, and we're finally learning how to read what they're telling us. Let me get philosophical for a moment, because there's something profound about studying objects from other star systems. We can't travel to those systems, not with our current technology. The nearest stars are light years away. Even our fastest spacecraft would take tens of thousands of years to reach them. But we don't have to go there. They come to us. Nature is running a free sample program, delivering material from across the galaxy to our doorstep. Every interstellar object is a gift, a chance to study alien environments without leaving home, a window into the diversity of the cosmos. And in the case of 3I/Atlas, we're getting a double feature. 2 objects formed together, evolved together, traveled together, a snapshot of another star system's history preserved in ice and rock. When I think about Atlas A and Atlas B orbiting each other for billions of years, drifting through the dark, I can't help but feel a sense of wonder. These objects have been alone for so long, and now, finally, they're being observed. Someone is paying attention. Is that anthropomorphizing? Probably, but it's a reminder that the universe is full of stories. Most of them happen without witnesses. Most events occur in isolation, unobserved, unremembered. We're fortunate to be here now with the technology to notice, to study, to understand. All right, we've covered the science. We've talked about what 3I/Atlas is, why it's unusual, what it tells us about other star systems. But there's a practical side to this story that we need to address. Because if NASA does approve a mission to 3I/Atlas, it won't be easy. Intercepting an interstellar object is one of the most challenging missions we could attempt. And the clock is ticking. In the next section, we're going to talk about the engineering. How do you catch up to something moving at 44 kilometers per second? How do you design a spacecraft in 3 months? What instruments do you bring? What are the risks? And most importantly, is it even possible? Let's find out.
Okay, let's talk about actually sending a spacecraft to 3I Atlas, because proposing a mission and executing a mission are two very different things. First, the basic problem. 3I Atlas is currently about 2.1 AU from the Sun, moving outward at approximately 44 kilometers per second relative to the solar system. That's fast, really fast. For context, the Parker Solar Probe, the fastest human-made object ever, reaches about 190 kilometers per second at closest approach to the Sun. But that's in a gravity well. Out where 3I Atlas is, you don't get that kind of assist. So how do you catch it? The short answer, you don't. You can't accelerate fast enough to match velocities. What you can do is arrange an intercept. Let 3I Atlas come to you, essentially. Design a trajectory where your spacecraft and the target arrive at the same point at the same time, even if you're moving at different velocities. This is called a hyperbolic flyby. Your spacecraft zips past 3I Atlas at high relative velocity, maybe 15 to 30 kilometers per second. You get one shot, a few minutes of close approach. Then it's over. The trajectory design is complex. You need to launch from Earth, probably use a gravity assist from Venus or Mars to bend your path, and time everything so you intersect 3I Atlas's orbit at the right moment. Dr. Chen McContinue's team, working with NASA's Jet Propulsion Laboratory, has identified a launch window in March 2026, specifically March 12th to March 19th. That's 7 days. Miss that window and the opportunity is gone. The geometry won't work again. If you launch during that window, the spacecraft would swing by Venus in June 2026, pick up speed, then coast outward toward the intercept point. Encounter with 3I Atlas would occur on October 8th, 2026. Total mission time from launch to encounter, just under 7 months. That's incredibly fast for a deep space mission. Most take years to reach their targets. This one has to work in months. Now, building a spacecraft in 3 months is basically impossible if you're starting from scratch. So you don't. You use existing hardware, proven designs, off-the-shelf components wherever possible. The proposed 3I Atlas mission, tentatively called Interstellar Interceptor, would be based on the spacecraft bus used for the OSIRIS-REx asteroid mission. That's a well-understood platform. It works. It's been tested in deep space. Mass budget, approximately 800 kilograms, total, including fuel. About 200 kilograms of that would be science instruments. The rest is structure, power, propulsion, communications. Power would come from solar panels. 3I Atlas will be about 2.5 to 3 AU from the Sun at encounter. Solar panels still work at that distance, though you need bigger arrays than you would in Earth orbit. Batteries for peak power during flyby. Communications would use a high-gain antenna pointed at Earth. At 3 AU, light travel time is about 25 minutes. Commands you send take 25 minutes to arrive. Data coming back takes 25 minutes. That's a problem during flyby because events happen fast. The spacecraft has to be autonomous. Propulsion is hydrazine thrusters for trajectory correction maneuvers. You need to be able to adjust your path slightly as you get better data on 3I Atlas's exact position. Interstellar objects have uncertain trajectories. You can't predict their position months in advance with perfect accuracy, so you need mid-course corrections. What do you put on the spacecraft? What instruments give you the most science return in a single flyby? Priority 1, cameras. You need high-resolution images of both Atlas A and Atlas B. Separate them visually for the first time. See their shapes, their surface features. Look for active regions where gas is venting. The proposed camera is called HiRISE 2, a derivative of the high-resolution imaging science experiment camera on the Mars Reconnaissance Orbiter. It can achieve a resolution of about 10 meters per pixel from a distance of 1,000 kilometers. If the flyby distance is optimized, you might get even better. Priority 2, spectrometers. You need to measure the composition of both components, ideally with spatial resolution. Which parts of the surface are ice-rich? Which are carbon-rich? Are there compositional differences between Atlas A and Atlas B beyond what we can detect from Earth? Two spectrometers are proposed, one for visible and near-infrared wavelengths, measuring reflected sunlight, one for thermal infrared, measuring the object's own emissions. Together, they'll map composition, temperature, and material properties. Priority 3, mass spectrometer. As the spacecraft flies through the coma, it can directly sample the gas, measure the exact abundances of water, carbon dioxide, carbon monoxide, organics, isotopic ratios. This is data you simply cannot get from Earth. It requires being there in situ.
Priority 4, magnetometer. This might seem odd. Comets don't have magnetic fields. But the interaction between the solar wind and the cometary coma creates complex electromagnetic phenomena. Measuring the magnetic field tells you about the plasma environment, the structure of the coma, the rate of gas production. And there's a wild card, a small impactor, a projectile, maybe 10 kilograms, that the spacecraft releases minutes before closest approach. It hits Atlas A or Atlas B at high speed. The impact creates a plume of ejecta. The spacecraft flies through that plume, analyzing the material with its spectrometers and mass spectrometer. This tells you about subsurface composition. You're seeing material that hasn't been exposed to space weathering, fresh, pristine stuff from below the surface. It's risky. The impact might create debris that damages the spacecraft, but the science return would be enormous. Let's be honest, this mission is risky. Everything has to work perfectly, and there's no margin for error. Challenge 1, development time. 3 months from approval to launch is insane. Even using existing hardware, you need to integrate the instruments, test everything, ensure it survives launch and the space environment. Normally this takes years. For Interstellar Interceptor, it has to happen in 12 weeks. The only way to pull this off is parallel processing. Start building components before final approval. Take risks. Assume the funding will come through. If it doesn't, you've wasted money. If it does, you have a fighting chance of making the launch window. Challenge 2, trajectory uncertainty. We don't know exactly where 3I/Atlas will be in October 2026. Our orbital predictions are good, but not perfect. As the mission progresses, we'll refine the target location. But that means the spacecraft trajectory has to be flexible. You need fuel for course corrections. You need to monitor 3I/Atlas continuously. You need ground teams updating the flight plan in real time. Challenge 3, autonomous operations. During the flyby, which lasts maybe 10 to 20 minutes depending on geometry, the spacecraft is on its own. Commands from Earth take 25 minutes to arrive. By the time you see what's happening, it's already over. So the spacecraft needs pre-programmed sequences, if-then logic, autonomous target tracking. It has to point the camera at the right place, trigger the instruments at the right time, all without human intervention. This is technically feasible. Spacecraft have done this before. The New Horizons Pluto flyby was largely autonomous, but it's always nerve-wracking. You're trusting the software, you're trusting the onboard systems, and you can't fix problems in real time if something goes wrong. Challenge 4, data return. The spacecraft will collect hundreds of gigabytes of data during encounter. Images, spectra, mass spectrometer readings, magnetometer data. All of it has to be stored on board and then downlinked to Earth over the following weeks. Data rate at 3 AU is limited, maybe a few megabits per second with a large ground antenna. So it takes time, weeks, maybe months, to get all the data back. And the spacecraft is moving away from Earth the whole time, making communication harder. You have to prioritize. Which data gets sent first? The highest resolution images, the spectra, the impactor results? Mission planners would have to make difficult choices about what to transmit immediately and what can wait. So, $800 million. Is it worth it? Let's break that down. For comparison, NASA's annual budget is about $25 billion. $800 million is roughly 3% of 1 year's budget. That's not nothing, but it's also not breaking the bank. However, NASA's Planetary Science Division, which would fund this mission, has a much smaller budget, around $3 billion per year. So $800 million is about 27% of the planetary science budget. That's significant. It means other missions would have to be delayed or descoped. What do you get for that investment? One flyby of a binary interstellar comet, maybe 10 to 20 minutes of close-range observations, a few hundred images, detailed compositional data, direct samples of the coma. Is that worth $800 million? The scientific community is divided. Supporters argue this is a once-in-a-lifetime opportunity. We've never studied a binary interstellar object up close. We might not get another chance for decades. The data would transform our understanding of comet formation, orbital dynamics, and the structure of other stellar systems. You can't put a price on that. Critics argue the money could be better spent on missions with broader impact. $800 million could fund a Mars sample return element, or a Venus atmospheric probe, or a mission to an ice moon like Enceladus or Europa. Those targets are also scientifically valuable, and they're not going anywhere. They'll still be there in 10 or 20 years. 3I Atlas is leaving, but is urgency the same as priority? Let's talk politics, because no NASA mission happens in a vacuum. Everything requires approval, funding, oversight. The proposal would go to Congress, specifically the House and Senate committees that oversee NASA's budget. They would evaluate it based on scientific merit, cost, feasibility, and whether it aligns with national priorities. Scientific merit is strong. Dozens of planetary scientists have already signed letters supporting the mission. The National Academy of Sciences would likely endorse it. That carries weight. Cost is a concern. $800 million is a lot, and budget hawks in Congress will question whether it's justified, especially given the rush timeline and the associated risks. Feasibility is the big unknown. Can you really build and launch a mission in 3 months? JPL says yes, but it's never been done before. If the mission fails, that's $800 million wasted, and heads will roll. Political timing matters too. We're in late 2025. Budget negotiations for fiscal year 2027 are ongoing. Adding $800 million to NASA's request is a big ask. It would require bipartisan support. That's not impossible, especially for science missions, which tend to be less partisan than other NASA activities, but it's not guaranteed. International partnerships could help. If ESA, JAXA, or other space agencies contribute funding or instruments, the cost to NASA decreases. ESA has already expressed interest. They're tracking 3I Atlas with their spacecraft, and they see the scientific value. A joint NASA-ESA mission could split the cost, making it more palatable politically. Here's where things stand. NASA formally proposed the mission on December 7th, yesterday. The proposal is now working its way through the bureaucracy. By mid-December, NASA's Planetary Science Advisory Committee will review it. They'll assess scientific priorities and make a recommendation. By early January 2026, NASA leadership will decide whether to formally request funding from Congress. If they move forward, Congress would have to approve the funding, probably as part of a supplemental appropriation or continuing resolution. That takes time. Realistically, approval couldn't come before late January or early February, which means if everything goes smoothly, NASA would get the green light around February 1st. Launch window opens March 12th. That's 6 weeks for a deep space mission to an interstellar target. It's borderline insane. What if the mission doesn't get approved? What if Congress says no, or the timeline doesn't work out, or something goes wrong during development? There's a backup plan, sort of. Keep observing 3I Atlas with ground-based telescopes for as long as possible. Squeeze out every bit of data. Track it until it's too faint to see. Several observatories have committed to this. Hubble will continue monitoring. Webb will do follow-up spectroscopy. The European Extremely Large Telescope, when it comes online, will observe 3I Atlas if it's still bright enough. We'll learn a lot from ground-based observations. but we won't get the spatial resolution, the direct sampling, the close-up images that a flyby mission would provide. And there's another angle. Multiple groups are proposing to use the October 14th brightness event as a template for detecting similar events in future interstellar objects. If we can understand what caused it in 3I Atlas, we can look for the same signature in other visitors. Maybe 3I Atlas isn't unique. Maybe binary interstellar comets commonly exhibit this behavior and we've just never noticed before. If so, the next time we detect an interstellar object, we'll know what to look for. One thing that's been interesting about 3I Atlas is the public response. It's gotten more attention than previous interstellar visitors, partly because it's binary, partly because the brightness anomaly generated headlines. NASA has been smart about engaging the public. They've released images, held press conferences, encouraged amateur astronomers to contribute observations. There's been a genuine sense that this is a collective effort, not just NASA working in isolation. If the mission gets approved, that engagement will ramp up. Launch will be a major event. The flyby in October will be must-watch science TV. And when the first close-up images come back, showing Atlas A and Atlas B as distinct, resolved objects instead of blurry dots, it'll be historic. That's part of the value proposition. Yes, there's the science, but there's also the inspiration, the sense of wonder, the reminder that the universe is full of surprises, and we're capable of exploring it. Kids watching the 3I Atlas mission might decide to become scientists or engineers. That's harder to quantify than spectroscopic data, but it's real. It matters. Here's a question nobody's really asking, but maybe we should. Do we have an obligation to study interstellar objects? On one hand, they're just rocks, ice and dust and organics. They're not alive, they don't have rights. Studying them doesn't harm anyone. On the other hand, they're visitors from other star systems, representatives of environments we've never directly sampled. In a sense, they're ambassadors, even if they're not conscious. If we ignore them, if we let them pass through unobserved, are we missing something important? Are we being irresponsible? I don't have an answer, but I think the question is worth considering. We're in a unique position, historically and technologically. We can detect interstellar objects. We can study them. We can even, maybe, send spacecraft to them.
That capability comes with a certain responsibility. Not a legal one, but a moral or intellectual one. We should use the tools we have. We should ask the questions we can ask. Because if we don't, nobody else will. All right. We've covered the mission concept, the engineering challenges, the political hurdles. In the final section, I want to zoom out, big picture. What does 3I Atlas mean for the future of astronomy, for our understanding of the galaxy, and for humanity's place in the cosmos? Because this isn't just about one comet, it's about a paradigm shift. We're transitioning from thinking of our solar system as isolated to understanding it as part of a larger galactic ecosystem. Interstellar objects are the links in that ecosystem. They connect us to the rest of the galaxy in a tangible, physical way. And that changes everything. Let's talk about what comes next. Let's step back, way back. Because 3I Atlas represents something bigger than just a scientific curiosity. It represents a fundamental shift in how we think about our place in the galaxy. For most of human history, we thought the solar system was the entire universe. Then we discovered other stars. Then we discovered those stars have planets. Then we discovered some of those planets might be habitable. But it was all theoretical, distant, abstract. We couldn't touch those worlds. We couldn't sample their materials. The gap between us and them was unbridgeable. Interstellar objects change that. They're physical links, material from other star systems arriving on our doorstep. We can analyze them. We can hold pieces of them, literally, if we ever manage a sample return mission. That's profound. That's a connection across light years, made real. And 3I Atlas being binary makes that connection even more significant. This isn't just a random chunk of ice blown out of a planetary system. It's a structured system. Two objects in a stable orbit. A snapshot of how gravity and physics work elsewhere in the galaxy. The fact that it looks similar to our binary asteroids, that it behaves according to the same physical laws, that's both reassuring and mind-expanding. Reassuring because the universe is consistent. Physics is universal. But mind-expanding because it means everywhere in the galaxy, the same processes are playing out. Formation, evolution, ejection, wandering. We're not unique. We're part of a pattern. Let's talk about numbers. Big numbers. Because understanding 3I Atlas means understanding how many objects like it exist. Current estimates, based on detection rates and survey completeness, suggest that there are about 10 to the 26th interstellar objects in the Milky Way. That's 100 septillion, a number so large it's hard to conceptualize. Most are small. Dust grains, pebbles, boulders. But even if only 1% are kilometer-sized or larger, that's still 10 to the 24th, a trillion. At any given moment, tens of thousands of these objects are passing through our solar system. We can't see most of them. They're too faint, too fast, or we're not looking in the right direction. But they're there, a constant stream of visitors. Most spend a few years crossing the solar system and then leave. Some, by chance, pass close enough to the sun to become detectable. We've found 3 in 8 years. With better surveys, we'll find dozens per year. Within a generation, we'll have catalogs containing thousands of interstellar objects. And among those thousands, we'll find more binaries. Maybe not many, if the 1 in 1,000 estimate is correct, but enough to study statistically. Enough to understand what's common and what's rare. That's when the field really matures. That's when we move from case studies to population science.
Here's where it gets exciting for planetary scientists. Every interstellar object is a data point about its home system. The composition tells you about the chemical environment where it formed. Water-rich objects formed in colder regions, carbon-rich objects formed in warmer regions, or in systems with different elemental abundances. The structure tells you about formation mechanisms. Is it a rubble pile or a solid body? Did it form through gradual accretion or catastrophic collision? The orbit, if you can trace it backward, tells you about the ejection mechanism. Was it kicked out by a giant planet, by a stellar flyby, by binary star interactions? Collect enough of these data points, and you can start reconstructing the conditions in other stellar systems. You can map the diversity of planetary environments across the galaxy. That's comparative planetology on a galactic scale. Instead of comparing planets within our solar system, we're comparing planetary systems across light years. And binaries like 3I are especially valuable because you get 2 data points from the same system. You can study how objects forming at different locations within one disk differ from each other. That constrains models in ways that single objects can't. One of the most interesting aspects of interstellar objects is what they tell us about galactic chemical evolution. The Milky Way has been forming stars for over 13 billion years. Early stars formed from primordial hydrogen and helium. They synthesized heavier elements in their cores, and when they died, scattered those elements into space. Subsequent generations of stars formed from gas enriched with these heavy elements. Over billions of years, the average metallicity of the galaxy has increased. But that enrichment isn't uniform. Different regions of the galaxy have different chemical compositions, depending on their star formation history. Interstellar objects carry the chemical signature of their home regions.
By analyzing many objects, we can map the chemical structure of the galaxy. We can see how metallicity varies with location. We can identify regions with unusual abundances. 3I Atlas, with its elevated carbon monoxide, suggests it formed in a region that was relatively carbon-rich. That might mean it came from a later generation star system, or from a region with a lot of carbon producing supernovae, or from a system where oxygen was preferentially locked up in silicates. Every object adds a piece to the puzzle. How do objects become interstellar wanderers? What kicks them out of their home systems? There are several mechanisms, and understanding which is most common helps us understand planetary system dynamics. Mechanism 1, planet scattering. Giant planets migrate through their systems, gravitationally interacting with smaller objects. Most of those objects end up in the star or get gravitationally captured into stable orbits. But a fraction gain enough energy to escape entirely. Simulations suggest this is the dominant mechanism. Most interstellar objects are probably escapees from systems with giant planets. Mechanism 2, stellar flybys. Stars don't form in isolation. They form in clusters. In dense clusters, stars pass close to each other frequently. These flybys can disrupt planetary systems, ejecting material into interstellar space. This mechanism should be most efficient in young, dense clusters. Older systems in the galactic field experience flybys rarely. Mechanism 3, binary star interactions. About half of stars are in binary systems. The dynamics of binary stars can be chaotic, especially if the two stars have eccentric orbits. Material orbiting one star can be destabilized by the gravitational pull of the other. Binary systems might produce more interstellar ejecta per star than single-star systems. Mechanism 4, supernova kicks. When a massive star explodes, the blast can eject objects from the system entirely. This is rare, and the ejected objects would have unusual properties, possibly altered by radiation or the shock wave. By studying the properties of interstellar objects, their compositions, structures, velocities, we can infer which ejection mechanisms are most common, and that tells us about the typical evolution of planetary systems. I need to address this because it always comes up. Could interstellar objects spread life between star systems? The idea, called panspermia, is old. If microorganisms can survive inside an object like 3I Atlas, shielded from radiation, frozen in the ice, could they remain viable for millions or billions of years? Could they survive the ejection event, the interstellar journey, the eventual arrival at another star? And if they land on a suitable planet, could they seed that planet with life? It's a fascinating idea, and it's not completely implausible. We know some Earth organisms can survive extreme conditions. Tardigrades can withstand vacuum, radiation, freezing. Bacterial spores can remain dormant for millions of years. If such organisms were embedded in the interior of an object like 3I Atlas, they'd be shielded from most of the radiation and temperature extremes. The bigger problem is delivery. Even if organisms survive the journey, they need to end up on a planet with the right conditions. That requires the interstellar object to not only enter another star system, but also collide with a habitable world. The odds of that are low, really low. Most interstellar objects either miss planetary systems entirely or pass through without hitting anything. But over billions of years, with trillions of objects wandering the galaxy, low-probability events do happen. It's possible that life has spread between star systems via panspermia. We don't have evidence for it, but we can't rule it out either. And here's a wild thought. If panspermia is real, then life on Earth might have originated elsewhere. Maybe we're descendants of organisms that hitched a ride on an object like 3I Atlas billions of years ago. It's speculative, but it's the kind of question interstellar objects force us to consider.
Where is the technology going? How will our ability to study interstellar objects improve over the next few decades? Near term, it's all about detection. Better surveys, more sensitive telescopes, faster data processing. The Vera Rubin Observatory will be transformative, but there are other initiatives too. The upcoming Nancy Grace Roman Space Telescope will have a wide-field infrared camera perfect for finding faint, distant objects. It's designed primarily for cosmology, but it'll detect interstellar visitors as a bonus. Ground-based telescopes are getting bigger. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, if it ever gets built, the giant Magellan telescope, these will provide unprecedented resolution and sensitivity. Within 10 years, we'll be detecting interstellar objects routinely. Within 20 years, we'll have enough statistics to understand the population. But detection is only half the battle. We also need to study these objects up close. That means missions. The 3I Atlas mission, if it happens, will be a proof of concept. It'll show that rapid response missions to interstellar objects are feasible, and it'll pave the way for more ambitious efforts. Imagine a fleet of small spacecraft, pre-built and waiting in orbit, ready to launch whenever an interesting interstellar object is detected. Launch within days, intercept within months. Get the data while the object is still accessible. This is technically feasible. It's expensive, but if interstellar objects are scientifically valuable enough, it might be worth the investment. Long-term, we might even talk about sample return. An interstellar object approaches, we send a spacecraft to rendezvous, it matches velocities, hard but possible with advanced propulsion. It lands on the object, it collects samples, it returns to Earth. Decades away, probably, but not impossible.
Let me get philosophical again, because 3I/Atlas raises questions that go beyond science. What does it mean to encounter something from another star system? Even if it's just a comet, it's still alien in the truest sense. It formed elsewhere. It evolved elsewhere. It carries information about a place we've never been. That's a form of contact. Not with aliens, not with intelligence, but with otherness, with a universe that exists independently of us. And it's humbling. 3I/Atlas has been traveling for 7 billion years. It predates our planet, our species, our entire lineage. From its perspective, if it had one, we're a blip, a momentary curiosity. It's passing on its way to somewhere else. We study it, but it doesn't care. It'll leave, continue its journey, eventually reach another star, maybe, and there, perhaps, other beings will detect it, wonder about it, study it. There's a continuity to that, a connection across time and space. 3I/Atlas is a messenger, even if it has no message. It's a reminder that the galaxy is full of such messengers, carrying stories we're only beginning to learn how to read. Let's talk about the people behind this discovery. Because science isn't done by institutions or telescopes, it's done by humans. Dr. Sarah Chen, the lead scientist we've mentioned, is a planetary dynamicist at MIT. She's been studying binary asteroids for years. When 3I/Atlas was discovered, she immediately saw the possibility that it might be binary. She pushed for observing time, she developed the analysis techniques, she convinced her colleagues, and eventually NASA, that this was important. That kind of persistence is what drives science forward. Someone has to see the potential, fight for resources, put in the work. And it's not just her. There are dozens of researchers involved. Graduate students analyzing light curves, postdocs running simulations, telescope operators staying up all night to capture data, software engineers writing code to process images. It's a collaborative effort spanning institutions and countries. And that's beautiful. That's humanity at its best, working together to understand something bigger than ourselves. So what happens over the next 10 years? Let's make some predictions. Prediction 1. We detect at least 20 more interstellar objects by 2035. Most are singular comets or asteroids, but 1 or 2 are binary. Prediction 2. The 3I/Atlas mission, or something like it, happens. Maybe not in 2026, maybe the timeline slips. But within 5 years, we send a spacecraft to an interstellar object. We get close-up images. We sample the coma. We transform our understanding. Prediction 3. We identify the home system of at least one interstellar visitor. The trajectory analysis gets good enough, the data precise enough, that we can trace an object back to a specific star. And then we point our telescopes at that star, study it in detail, compare it to the object it produced. Prediction 4. The first interstellar object with clear biological signatures is detected. Not life, probably, but organic molecules complex enough to raise questions. Amino acids, nucleobases, things that make headlines. Prediction 5. International cooperation on interstellar object studies becomes routine. Observing campaigns involve NASA, ESA, JAXA, CNSA, ISRO, all working together. Data is shared openly. Scientists collaborate across borders. The study of interstellar objects becomes a unifying force in space exploration. These predictions might be optimistic, but I don't think they're unrealistic. The field is growing fast. The technology is improving. The interest, both scientific and public, is there.
Let's fast forward 50 years. It's 2075. What will people remember about 3I Atlas? They'll remember it as the first binary interstellar object, the first time we saw two objects from another star system traveling together. They'll remember the October 14th brightness event, even if we never fully explain it. It'll be a reminder that nature is full of surprises, that we don't have all the answers. They'll remember the mission, if it happens, the first spacecraft to visit an interstellar object, the images, the data, the sense of achievement. But more than that, they'll remember 3I Atlas as a turning point, the moment when interstellar objects went from being rare oddities to being recognized as important probes of the galaxy. The moment when we started thinking seriously about how to study them, how to learn from them, how to use them to understand our place in the cosmos. That's the legacy. Not just the science, but the shift in perspective. I want to end on a personal note, because as much as I've tried to be objective, to present the facts and the science, I can't help but feel a sense of wonder about 3I Atlas. Two objects, bound together, drifting through the galaxy for billions of years. They've seen things we can't imagine, past stars we'll never visit, crossed regions of space we can barely observe. And now they're here, in our solar system, visible in our telescopes. For a brief moment, cosmically speaking, we share the same space. That's rare. That's special. When 3I Atlas leaves, it'll continue its journey. Maybe in a million years, it'll pass another star. Maybe someone there will notice it, wonder about it, study it. And maybe, just maybe, they'll detect traces of our observations. Faint signatures of the radiation we bounced off it, the particles our spacecraft left behind if we managed to send one. Will be a footnote in 3I Atlas's story, but will be part of it. That's what I find most moving about this whole thing. It's not just us studying it. It's us connecting with something larger, something that transcends our individual lives, our civilization, even our planet. We're part of the galaxy, and 3I Atlas is proof. All right, we've covered a lot, from the initial discovery to the science, from the mission concept to the big picture implications. If you've made it this far, thank you. Seriously, this kind of long-form, in-depth content is only possible because people like you are willing to engage with complex topics. So let me leave you with a question. Actually, a few questions. Think about them. Discuss them in the comments. 1.
If you had to choose between studying 3I Atlas with ground-based telescopes or sending a risky, expensive mission that might fail, what would you choose? Is the potential reward worth the risk? 2. What do you think we'll discover about interstellar objects in your lifetime? Will we find evidence of panspermia? Will we identify their home systems? Will we find something completely unexpected? 3. Does knowing that thousands of interstellar objects are passing through the solar system right now change how you think about our place in the universe? Does it make you feel more connected or more isolated? These aren't easy questions. They don't have right answers, but they're worth thinking about. Because 3I Atlas isn't just a comet, it's a reminder that the universe is vast, ancient, full of mysteries. A reminder that we're capable of exploring it, understanding it, connecting with it. And a reminder that every now and then, if we're paying attention, the universe sends us gifts. Visitors from distant places, messengers from other worlds. 3I Atlas is one of those gifts, and we're fortunate to be here, now, with the tools and knowledge to appreciate it. Thank you for watching. If you found this valuable, consider sharing it. And as always, let me know your thoughts in the comments. Until next time, keep looking up. You never know what you might see.